Okay, let's let's write it down because this is something you have to memorize for the test, and it really starts out, and you guys can kind of get familiar with it as you read it. But I'm going to put it on the board, and we're going to talk about it. It really says, let f be a function defined on an interval and then when I taught you the song, yeah, but I have to put it back on the board, and then read it over, kind of look at it as we go, and we're going to start to put it on the board here. So let f be a function defined on an interval, maybe not at a. So, and the idea is that you can actually, I want to set you guys up to where if you draw this, you can then understand what it's saying. So what should I draw at this point? Yeah, some type of a line, curve, function. And maybe not at A, so I have to put A there as a point that's, it might not be defined. So I could put an open circle there. Now, the song goes that then we have a limit. So the whole idea is that we want this limit, then the limit as what? X approaches A of f of x is equal to L. What should I draw there? Yeah, I should draw the output of L. Now this is the really important part. This is where we said stop. Let's get serious. Because now we get down to the nitty-gritty. We say there exists what? Epsilon that is greater than 0 for every delta greater than 0. Such that, now this is the really important part, guys. I want you to understand this. This is all about the distance. So the absolute value of f of x minus L is less than epsilon. What this means is the distance of f of x from the limit. So how far we are from the limit. That's your epsilon value. So I can now draw this portion. So this would be your limit plus epsilon, if you don't have that yet. And then I would draw a spot below it, which would be the limit minus epsilon. No, epsilon would refer to a very small number in this situation, which often occurs in mathematics. Sigma would be the large S, capital S, which looks kind of like the small epsilon, but that would mean some. So very different. So, such that, given this happens whenever we have 0 is less than x minus a, which is less than delta. This is also a distance. Remember, distance is the absolute value of something from another object. So whether that's you're negative 2 units from it, then your distance would be 2. So that's all this is the distance. So where does this go? This goes along the x-axis. So this would be a minus delta, and this would be a plus delta. Delta is the small difference in the x values of how far you are from that number. And the whole idea is this. Remember yesterday when we said, how can we guarantee that we are within 100th or 1,000th of the limit? We all started with this problem up here with the line. And we said, how close would you have to get to x equals 3 in order to ensure that the output was within 100th? We want to be within 100th. And you guys all said that we would have to get to within a distance of 0.005. Remember that? And what we want to do is we want to run this from 0.05 to infinitely small. And so, like I said, there's going to be 3 levels to these type of problems in the book. We're just going to go to 1.5. And the most important thing that you do is, number 1, can you understand this drawing as we see it? Epsilon is for the outputs. You got that? Delta is for the inputs. As long as I plug in a number within these boundaries, I will get an output within these boundaries. And when we force this closer together, that delta value closer to 0, these values will get closer to what? L. Yep, your output value become very close to L. And that's what we want. We want to force these things together. Because we don't know, I mean, this is a nice function. It's well behaved. But what if it got really wonky like we were talking about yesterday? Then who knows what happens. So flip it over. Let's actually try an example here. Going to have your graphing calculator. You do have a graphing calculator. Okay, so this is kind of the this is a step 1 process. We did one yesterday where we looked at an example of a line. This would also be kind of a more refined process. What we're going to do is we're really just going to try to state our epsilon and delta values. We're just going to really take our drawing and apply it to this. So first it says consider the function f of x equals 1 over 2x. Now when you type this into your calculator, make sure that you put parentheses on the bottom. Everybody do that right now, and let's try to make sure that we have a good picture of what this thing actually looks like. Thanks, bro. And I'm going to zoom standard, zoom 6. Kind of see it? Get an idea? You've got vertical asymptote at 0, horizontal asymptote at 0. So we'll draw a sketch of that, and then we'll zoom in to get a better look at it. So first we just get a general sketch. So the graph looks like this. So the first question is on the test, could you sketch a graph of a function? I would hope so. All right? And now I'm going to start to label things. This is f of x is equal to 1 over 2x. Now, let's read the problem. Find an interval for x values such that the y values will always be within 2/10 of the limit as x approaches 2. A for the day. What is the a value? A is always what I am approaching. I'm approaching 2. That's my a value. So I'm going to put that right here. 1, 2, 1, 2. So I have 2 right there. Is the function defined at 2? If I plugged it in, would I get something? Yes. So we actually know the limit. We know that the limit as x approaches 2 of 1 over 2x is equal to what? 1/4. Because you can plug 2 in. 1 over 2 times 2 is 1 over 4. Now, could you actually prove that that is true? I mean, we plugged it in, but could we prove that that is true? Question. Limit is the value that the outputs are approaching. So if you plug in, remember when we plugged in numbers really close, like 1 and 1.5 and 1.9 and 1.999? The outputs got really close to this. And then we tried it from the other side. We tried plugging in 3, 2.5, 2.1, 2.01, 2.001, and we got really close to 0.25. It's the number that you're approaching from the left and the right. The y value, the output that you're approaching from the left and the right. And in order for the limit to exist, the left hand has to equal the right hand. Okay, so we have that. Now, let's draw this, okay? Here's kind of our definition piece. It says the absolute value of f of x minus the limit has to be less than epsilon. That's what it's saying. So I'm going to use my definition. You have to know that. We have to be able to use it. Well, what is my function? 1 over 2x minus, what is the limit? What do we state that it is? 1/4 is less than epsilon. What is the distance from the limit that we're trying to stay within? 0.2. My tick marks aren't doing a very good job here, so I'm going to adjust them. But if you plug in 2, we said you get an output of 1/4 or 0.25. And it's saying that we want to find new boundaries, all right, so that we are within 0.2. So what would be the largest y value that we could achieve? What? What would be the largest y value we could achieve? No. I have a boundary of 0.2. 0.45, L on. 0.45. The epsilon value is 0.2. So a distance of 0.2 from that spot. Right there. Okay. Everybody's got it. Now, what would be the lowest boundary I could have? 0.05. So, this must satisfy something. We said that you have this, and this must satisfy whenever, we had another part here, the distance of x from A has to be less than, starts with D, rhymes with delta. Delta. Very good. So, so if that's a D, delta would start at that same place and kind of come up, but then it kind of swings around like that. Almost like an eighth note. Sure. That'll be a delta. So I don't have, I'm choosing x values. What is my A value? What is my A value? 2. Okay? Is less than delta. That's what we're wondering. We are wondering how close to 2 do we have to be in order to ensure that our outputs are going to be within 2/10 of the limit. So we want to find these delta values. So we don't know what this is. This is some distance. Obviously, you can see if our drawing is correct that one is a lot smaller than the other. But we want to try to come up with these so we can assure that we are going to be within that correct output. So here's what we do. We have our function. We are now going to graph our upper boundary and our lower boundary, and we're just going to look for those points where they intersect. And if we can find those points where they intersect, then we know our boundaries. So I'm looking at, do you see how I got 0.45? Where 0.45 runs right through my function, and where 0.05 runs right through my function. Take out your calculators. Let's change our window a little bit. We have to know how to do this. We go into our window, all right? We're going to have our x maximum go all the way to 10 because we don't really know how far out we have to go. But our x minimum, -1 would be fine, all right? Now, how about our y minimum? Do we go below the y-axis? No, so I'm just putting -1 so that, probably -0.1 would be fine. Anything like that would be fine. Just to kind of get that bottom axis part. And then what's the maximum y value that we're even talking about here? 0.45. So if I go up to 1, that would be plenty, right? That'll be plenty. Everybody got their window? You have to be able to think about that and generate those values. I go into y equals, and I have my function. I'm also going to type in my two upper boundaries. They are horizontal lines, so they have equations y equals what? 0.45, and y is equal to 0.05. And so I now have those boundaries, and I press graph, and you can see there I have my function, and look at, I got my top boundary. Oh, did I catch it? It doesn't look like, I maybe have to extend x a little bit further, don't I? So let's go to our window. Instead of 10, let's go up to 20. And I don't want to see so many tick marks, so I'm going to change my scale to 20 as well. That way I don't see so many tick marks. And we'll try it again. I press graph. And looks like I have my top one. Did I catch the bottom one now? Yeah, we're good to go. So all I want to know is those intersection points. Because if we know where this x value is for the intersection, that will tell you how far we are from 2. And if we know this x value of our intersection, then we will know how far we are from 2 as well. So you have a nice intersection button on your calculator. We could just go second, calculate, and what do I select? Number 5. It's right on your trace. So it's asking which is the first curve, and I can't really tell where I'm at. It looks like I just moved left to right. It looks like I'm on 1 over 2x. So I'll select that one. I'll press enter. Do I want to find the intersection between 1 over 2x and that guy? Yeah. So I press enter on that. And do I want to guess? No. And it finds it. What is my x value? 1.11. Okay, hey, if you don't know how I did it, you're gonna learn again, because we're gonna do the same thing right now. So let's go back to our calculator, and I'm just gonna hit the graph, so I see the graph, and now we want to find the other intersection. Question. Sure, table's fine as long as you end up on an integer value. I mean, it showed up, but is that an approximation or is it the exact value? Okay, but so you were able to table exactly 1.111. Okay, that might not always happen depending on your delta value. So let's change this. All right, now we want to know 1 over 2x, and then this bottom one, which is 0.05. So I go second, calculate. TJ, you tell me if you're doing okay. Now at 5. Now, am I on the curve? Am I on the curve 1 over 2x? I am, so I press enter. When I do, it jumps to which one? It even tells you y sub 2 is 0.45. I don't want that one, so I press down to toggle. Second curve, y sub 3 equals 0.05. Do I want that one? Yeah, so I can press enter on that. I don't want to guess. And you can see it's going to run the intersection point out to here. X is 10, Y is 0.05. Question. Yes, you can. You can solve it algebraically. Some of the functions that we get to, you won't be able to solve algebraically. This one you sure can. You need to toggle down to your next function. So watch again, Derek. So I go second, calculate. I grab number 5 for intersect. My first curve, it says 1 over 2x. Is that what I want? Yep, I need that when I press enter. Look at what it does now, Derek. It says 0.45. I don't want 0.45. I press down, and it toggles to 0.05. I press enter and enter, and now I have 10 and 0.5. So we're almost done. We're almost done. Delta represents the distance from 2. What is the distance from 2? 0.8 repeating. Because you take 2 minus 1.11111111. 2 minus 1.11111 gives me 0.8 repeating. Now, what is the distance from 10 to 2? 8. So I have to take the larger. I really have to take the larger. All right? We know that this interval, we know that the interval from 1.11, comma 10 will give us outputs. But we have to choose an appropriate delta value. So back up here, what delta value? We got to choose the larger one, 8. So as long as you're within 8 units of the number 2, your outputs, will be within, or no, I'm sorry. We got to choose a smaller one. I'm sorry, smaller one. You choose a smaller one. Sorry. Yes, sorry. Smaller delta values. We have 0.8 repeating, and we have delta equals 10. We choose, delta equals 8. We choose the smaller of the values. So if I go 0.8 away from 2, you can tell that my output is within 2/10. If I go 0.8 away from here, you can tell again I'm going to be within that 2/10. So all we did is we found the upper and lower boundary. That was it. No, you wouldn't. Let's try another one that's a little bit more difficult, okay? All right, and then tomorrow we'll practice this in class, okay? I don't want to overwhelm you with this stuff. I want you to be able to become familiar with it so that you can do it someday. And then Friday we can actually get to the proof portion. Yes. Right here. The question says, find the interval for x values. Well, this interval right here, this is technically an interval. 0.8 to one side of 2 and 0.8 to the other side of 2. So that's your interval. Okay? All right. All right, let's go to our calculator. Let's get a view of this function. We go to y equals. This one is 3 sine of 2x, so I should make sure I'm working in mode. Am I in radians? I am, so I'm good to go. Y equals. We have 3 sine of 2x. 3 sine of 2x. And I'm going to zoom standard. Pretty cool, right? I want to approach pi over 8, okay? X is approaching pi over 8. Let's zoom in on that region. Pi over 8, so pi is about 3. 3 over 8, it's less than 1/2. So I don't have to have just a huge viewing window. So I'm going to zoom here as a box this time. So I don't care what method you use to zoom in on this area, but you need to do something, okay? And to answer Andrew's question, if you can solve this stuff algebraically, you can do that. Enter. I'm going to go down, and my x values only need to go over to, if I went over to 1, that would be plenty far. So I'm just going to press enter there, and I'm going to generate a new graph. And that's what I'm going to draw down on my paper. Okay? So 1, 2, 3, it looks like it goes up to. Now, we'll see how well you remember your trig. In order to find the period of sine or cosine, I take 2 pi and divide it by your b value. What's your b value? 2. 3 represents your amplitude, which is 3 units high. You guys need your trig notes back, don't you? I'll print them off for you tomorrow. So our period is pi. So watch this, you guys. Let's just, so that we understand. If you have a sine function that looks like that, and this is pi, what is halfway going to be? Pi over 2. What's a quarter of the way going to be? So we know that that spot right there is going to be pi over 4. So where's pi over 8? Halfway in between there, very good. And that is my A value. Is the function defined at pi over 8? Yes. So we have the limit as x approaches what? Pi over 8 of our function 3 sine of 2x is equal to, we need a value, right? Easy to do that. I'll show you another way to do that on your calculator. Second, calculate, simply value. Hit enter. X is equal to, just punch in, pi divided by 8. And it will give you a y value of 2.12. Second, calculate value, number 1. And you do pi divided by 8. And we get 2.12. That's my output. I'm going to mark it. 2.12. Stop. So here we have it. Let's write down our definition. The absolute value of what? F of x minus the limit has to be less than epsilon. Let's plug them in. What's our function? 3 sine of 2x minus what's the limit? 2.12. Has to be less than, what is epsilon? 0.1. Let's graph that. What's my upper boundary going to be? Which is 2.22. Thank you. Yep, 0.1. So I have 2.22 on top. What do I have on the bottom? I have 2.02. And so these are going to correspond to delta values on the bottom. So my delta expression is x minus what? A. Absolute value of that has to be less than delta. We're choosing x values minus our a value is pi over 8. And we are going to now find our delta, and that will be the interval which we can guarantee those outputs. So we're going to find that. Now I go to my calculator. What do I type into y equals? 2.22 and 2.02. And I hit graph. Did I catch both of them? I did. So now I just need those intersections. Second, calculate intersection number 5. And that is a curve that I want to use. And it looks like it's going to do the top line first. That's fine. I won't guess. If there's more than one intersection point between a curve and another curve, then you guess, you move it closer. So then it knows where it should guess. X is 0.416, 0.417. So it looks like this value right here is 0.417. I need my other value. So I go second, calculate, and I do 5 intersection. First curve, is that my curve? If you can't tell, you can look up here, it tells you. And is that my second curve? No, so I toggle down, I grab the next one. We'll finish here, guys. I promise. It's going to go real quick. We got 0.369. So the question is, what is my distance from pi over 8? Well, if you take pi and divide it by 8, you get 0.393. So how far are each of these from that? Well, 0.417 minus 0.393 is 0.024. And if you do 0.393 minus 0.369, you get 0.024. So they're about the same, right? So my delta value is 0.024. That's all the closer I have to get to x in order to ensure that the output is within 1/10. So tomorrow, before we do the proof part, tomorrow I want to practice this in class. Okay, are you capable of practicing this now? Is it starting to make more sense? Okay, so let's enjoy tomorrow. Tomorrow we'll practice the song right away as well so we can record on Friday. T-Shaw, be ready to freestyle.